Hello, everyone. Thanks for joining us today. This is our first seminar of the year, and it's going to be presented by Professor Supriyo Mitra. Okay, Supriyo, so the floor is yours.
Okay. Thank you very much, Daniel, for inviting me to this webinar. What I'm going to talk about today is an experiment that we had started more than 10 years back. And this has been a collaborative effort between my institute, IASER Kolkata, the Sri Mata Vaishno Devi University in Katra in Jammu and Kashmir Himalayas, and the Bullard Labs University of Cambridge. So this has been funded through multiple international collaborative projects, the UKIERI, the NERC, IOF, IAA, UGC, UKIERI, and the Royal Society International Collaboration. At the onset, I must also acknowledge the contributions from my collaborators, PhD students Swati Sharma and Devarshan Pauli, based at IISER Kolkata and SMBDU, undergraduate students Shubham and Oyon, and postdoc Shamim. Also, Ashling Oken, who had been a PhD student at Cambridge with Alex, Keith, and Sunil Wanchu from SMBDU. So I'm going to talk about the 3D crustal structure, earthquakes, and ground motion simulation in the Jammu and Kashmir Himalayas. Here is a broad outline. So I'll first tell you about the motivation and the objectives of the work. Then I'll briefly introduce you to the experiment called JAXNet. I'll primarily talk about the 3D velocity structure that we obtained from this experiment, the data from this experiment. Then quickly touch upon the earthquakes, and then show you how Ashling and Alex combined all of this information to simulate ground motions. All of this work has been published over the last few years. So if you wanted to read more about it, here are the references. To start with, let me first introduce you to the Himalayas, which is basically in the northern part of India. The Himalayas have been built through continent collision between India and Tibet, which happens or continues in the present day, accommodating a convergence of about 20 millimeters per year between India and Tibet, which is accommodated within the Himalayan belt. What you see as these blue numbers on top are in millimeters per year. You can see that there is a lateral variation in the convergence rate that happens across the Himalayas. And the arrows shows you approximately the direction in which the convergence is happening in the India fixed reference frame. This convergence is obviously accommodated within the Himalayas by buildup of elastic strain, which results in earthquakes. What you see as these ovals with numbers are basically the earthquakes which have been. This is over the last few centuries. There are few recent ones, like the 2005 Kashmir earthquake, which is at the northwestern edge, 2015 Nepal, which is somewhere in the middle. There are certain regions where there hasn't been a big earthquake in the last 500 years, which are these gray regions, which we call as seismic gaps. But they're not really gaps in earthquakes in the sense that there hasn't been a big earthquake, but these regions are accumulating elastic strain and will produce big earthquakes in the future. Our interest was in one of these seismic gaps, which is in the northwestern corner, which is marked by the red box. So if I take a closer look at this region, this is a gap between the 2005 Kashmir earthquake, which you see on the left of your screen on top, and the 1905 Kangra earthquake, both greater than 7.5 magnitude. This region had a big earthquake in 1555. And what you see as the red oval is the mesoseismal zone of that earthquake in 1555. So the current 11 millimeters per year, which obviously has accumulated about 5 meters of slip over the last close to 468 years, and has the potential to drive an 8 magnitude earthquake if the entire seismic gap broke in a big earthquake. So this is the region that we wish to study. The lithotectonic units across this region, going from south to the northeast, you have the Himalayan foreland basin, which is basically in the front of the mountain belts. Then you have the sub-Himalayas, the lesser Himalayas, the higher Himalayas, and the Tethyan Himalayas. If you took a cross-section and looked at the topography across this region in the east, which we refer as the Jammu-Kishtwar Himalayas, you can see that there is this Kishtwar window, which is marked in blue in the map, is a geological window which exposes lesser Himalayan deeper rocks within the higher Himalayas. If you move towards the northwest, the three main units are the Pir Panjal Ranges, the Kashmir Valley, and the Zanskar Ranges. Again, if you take a cross section across that region, look at the topography, what you see is a piggyback basin, which is the Kashmir Valley, which is sitting in between the two high ranges of the Pir Panjal to the southwest and the Zanskar to the northeast. Now, when we started studying this region, there was no knowledge of what the subsurface structure was. So we didn't know what was underneath these regions. What we could clearly see is that the geology and the topography between these two regions varied. And we wanted to understand what was going on underneath these regions. With this, we set out an experiment which is called the Jammu and Kashmir Seismological Network, or JAXNet, which eventually had 32 broadband seismograph stations running in this region, which are shown on the map as colored triangles. You can ignore the different colors. They are essentially telling you when the stations went in, but eventually there were 32 of them running across this region, and as I said, funded through various projects. The objectives were to look at the structure, then use the structure to look at the earthquake sources, look at their mechanisms, try and understand the geometry of the main Himalayan thrust, which is the main fault which causes big earthquakes underneath the Himalayas, and also where it comes out to the front. Use local earthquakes to look at the attenuation structure so as to understand how waves are going to propagate in the medium once you have a big earthquake, and then combine all of these to look at ground motion simulations. So today what I'm going to do is I'm going to use a subset of this data and talk about the structure, earthquakes, and the ground motion simulation. Here is a map which shows you the subset of the data that we are going to that we have used, which is these green triangles. What you can see is that they are mostly concentrated in that Jammu-Kishtwar region, and we had a few stations towards the northwest. Just to give you an example of what these sites look like, as you all know that the Himalayas are not an easy terrain to do field work and set up seismometers, and more so in the Jammu Kashmir region, which is kind of even more difficult, being at the northwestern edge of the Himalayas. So this is one station at the site called SMVDU, which is close to where Sunil Wanchu is based. So this is what a typical station looks like. And the reason why I put up this slide is to also, again, acknowledge the fact that this experiment went on ground and was maintained by the students and the postdocs, without whom we could not have done it. And they're all listed here. Once you set out an experiment like this, the first thing that you ask is how good are the stations? So a standard way of looking at the performance of the station is to calculate power spectral density, probability density functions, which are calculated. I'm showing you two examples, one from a station called Aknur, which is in the spheric sediments in the south, and one in the sub-Himalayas, which is on hard rock in the site called SMVDU. You are looking at the central panel, which is basically the vertical component PSDPDFs, which have been calculated for a data taken over 30 days. And the way you compare it is by looking at the performance of the station of the data, which lies within the USGS new low noise and high noise models. And you can clearly see that all our data actually falls within the two bounds. So our stations had very good deployments. They perform pretty well. The other thing that I wanted to highlight here is because we have two different stations, one on the sediments, one on hard rock. If you look at the histograms, which are plotted on the right for a particular frequency or a period, which is basically drawing vertical lines on the central panel, you can see that at 10 Hertz, which are the black histograms, there is a difference in the performance on the sediments vis-a-vis the hard rock. The sediments obviously produce larger high frequency noise, which is larger by about 10 decibels. So this is kind of the standard performance that you see across stations in the Himalayas. Now, once we had done this, obviously this experiment recorded data, which were earthquakes and ambient noise in between earthquakes. So we intended to use everything, starting from the body waves, the surface waves, the coda waves, and the ambient noise. The way we do this is we use body waves primarily to study the source of these earthquakes. Then we use body wave conversions and reverberations, along with the dispersion that we abstract out of the surface waves to look at the earth structure. We use the coda part of the local waveforms to look at its temporal decay and understand what the attenuation characteristics is. We have done this in 2D and 3D. And then we use the ambient noise, abstract surface wave by doing noise cross correlation, and then feed them back into the dispersion, which then helps us in refining the earth structure at a shallower level. once we have got all of these done, then Alex and Ashling comes in and does their field work, looks at active structures, and then they use all the information that we have acquired through the seismology, combines it with the field observations to do ground motion simulations. So today I'm going to show you our results on the Earth structure, show you a bit about the source, and then about the ground motion simulations by combining with field observations. So the way we look at the structure is one of the standard ways that people have done it is using receiver functions. We use earthquakes, which are at teleseismic distance. So you see the globe on the right shows you, the red dot shows you the earthquakes that we have used. The triangle shows the approximate location of the experiment. So these earthquakes lie at a distance between 30 and 90 degrees. These are greater than 5 magnitude earthquakes. I'll spend one slide in telling you what these receiver functions are. So if you have an earthquake which is at teleseismic distance, shown by the cartoon in 1, this energy travels from the source to the receiver, and it interacts with the structure underneath the site. So what it does is it transmits, converts from P to S, and reverberates within the structure. If you were to do signal processing on the waveform by removing or deconvolving the vertical component from the radial and the tangential, what you end up with are radial receiver functions and tangential receiver function. I'm showing you one example in 3 for the ray path that you have in 2. So this is what a radial receiver function would look like, where you have the last leg of S wave recorded. So these are the reverberations and conversions underneath the site. So you'll have the PS phase, which is the P to S conversion underneath the station. Then you have PPPS, which is basically a reverberation of 2 legs of P and an S. And then you have other reverberations. If you could actually model the amplitude of these arrivals, that would give you a constraint on the impedance contrast across the boundary from where you have these reverberations and conversions. If you knew the velocity structure, then you could use the time offsets to look at the thickness of the layers. And I'll show you how we do this. If I move forward, here is a map which shows you all the stations and the data that we have used. What you see on the left are basically the triangles where the stations are. And then for a beam of ray coming from different earthquakes, they will actually pierce through the structure underneath the site. And if you see the cartoon in the center top, this shows you these different rays which are piercing through the structure, reaching your station. So they will basically see all these different impedance contrast interfaces, MOHO being one of the strongest one. What we did was, we, rather than looking at the piercing points of the MOHO, we wanted to look at the piercing points at a mid-crustal level, which is about 30 kilometers depth. A standard way of looking at receiver functions are to kind of stack them by small bins in back azimuth and distance for every station. However, we had a lot of overlapping piercing points, which you can see in these circles that are plotted on the left map. For every triangle, the circles are color coded, which tells you that these are piercing points for rays recorded at that particular triangle. Because there was overlap between all these piercing points, and also there were some regions where there were gaps. The way we thought of doing this is not by collecting them by stations, rather than collecting them by piercing points. And therefore, we broke our region up into 2D grids of 0.1 degree by 0.1 degree. And then the question that we asked is, what are the piercing points, irrespective of the station, which falls within that grid? And we look at all the receiver functions for, let's say, this example grid, which I show in blue. And these are all the receiver functions which are piercing within that grid. And we say that we will stack all of these and model them, which will represent the structure underneath that grid. And we do this for every grid. So we stack all these receiver functions, and what you see on your bottom left is the plus minus 1 standard deviation of the stacked receiver function shown in black. And then what we do is we model this stack along with surface wave derived dispersion data, which we take from Gilligan and Priestley, which is plotted on the bottom right. And we ask this question, that is there a velocity model which will fit both these data sets equally well? And we put in weights to the different data sets. We weigh the receiver functions a bit more than the dispersion data. And then we derive velocity models which will fit both the data sets equally well. We do this by first thinly parameterizing the velocity model. So what you see on the right top is a thinly parameterized velocity model in blue. So you have depth versus shear wave velocity. And then once we have a good fit to both the receiver function and the dispersion data, we try and coalesce layers which have similar velocities to form a thickly parameterized model, which is in red. And you can clearly see that both the red and the blue model fits the receiver function and the dispersion data equally well. So once you have done this, so you have got a 1D structure underneath the example grid that I have, and you repeat this process for every grid that's there in this region. Therefore, you have 1D models underneath each of these grids. Then you can combine them to form 3D velocity models, and that is what I'm going to present. But before I get there, what I'll do is I'll first present to you two cross sections which runs across the strike of the Himalayas, going from southwest to the northeast. The first one, which runs across the Jammu-Kishtawar region, which is my profile A1, A2. And then I'll talk about the B1, B2, which goes across the Kashmir Valley, which is the BWAC basin. The way I'm going to present these results is first I'll show you what the receiver function spatial stack looks like. Then I'll do a common conversion point CCP stack, where you essentially collapse the energy onto a 2D plane and look at where you have the conversions, where the maximum energy is from, and then you kind of color code them. And then I'll show you 2D velocity profile out of the 3D model, and I'll compare all the three to show you what it highlights about the structure underneath the site. So let me start with the Jammu-Kishtawar Himalayas. What you're seeing is that A1, A2 profile on your left is southwest, on your right is northeast. You see all these receiver functions which have been spatially stacked in narrow bins across this region. What you see as positive arrivals are colored as red. So your MOHO would be a positive impedance contrast boundary. Similarly, you'll have a mid-crustal boundary where there is increase in velocity, positive impedance contrast plotted in red. The negative impedance contrast boundaries are plotted in blue. So it's not straightforward to read these kind of plots. Therefore, what we do is we convert them into common conversion point stacking, which is like a migration along the ray path and then looking at the conversions at depth. And here is a CCP stack. So again, here red is positive velocity increase or positive impedance contrast, and blue is negative impedance contrast velocity decrease. On top of this, what I've also plotted here are all the earthquakes that had been located by Paul et al. Using the network data that we have, and also Ashling, where Ashling's earthquakes are actually plotted in green. She also had a constraint on the dip of the plane on which the earthquake happened. Therefore, you have these bars on top of the green circles, which shows you the dip of the plane. So on top of that, what I've also put are the MOHO depths which have been obtained by individually inverting the receiver functions underneath the stations, which was Swati's PhD work, so as to compare my way of doing it, where we do it in 2D grids, vis-a-vis the station stacked receiver function MOHO depth. And you can see that they kind of match closely. So I'll highlight the main features on this cross section here. What you see is a two-layer Indian crust, which is under thrusting the Himalayas from the left to the right, which is about 40 kilometers thick. What you also see is that the MOHO has an overall northward dip with certain undulations underneath the higher Himalayas and with southward dips in certain sections. What you also see on top, which is the negative impedance contrast, is the MHT, which is called the main Himalayan thrust, which is the top of the downgoing Indian plate and the boundary between the overriding Himalayas and the downgoing Indian plate. It's a negative impedance contrast boundary. The reason why it's negative is because you are actually putting deeper crustal material on a thrust fault across that region. Also, it's a fault gouge, therefore you have material contrasts, and there is most probably some fluids, which reduces the velocity in that layer. So you can see that MHT flat, which basically marks the top of the downgoing Indian plate, has a 4-degree dip beneath the sub-Himalayas and the lesser Himalayas, and then you have a ramp, which is of a higher dip, which is about 13 to 17 degrees. If you look at the top of this MHT in the region to your right, which is in the northeast, underneath the Kishtwar window, you see that the earthquake planes are dipping steeply, and they more or less align with some structure which is steeply dipping. In the Himalayas in Nepal and in Sikkim, people have actually, structural geologists primarily, have talked about lesser Himalayan duplexes, which helps in accommodating the convergence. And that is one of the reasons why you have the lesser Himalayas showing through the Kishtwar window. And we think that what we are seeing in the structure and in the earthquakes is the active lesser Himalayan duplex underneath the Jammu-Kishtwar region. Now, if I move forward and show you the 2D velocity structure, here you have the scale on the right. So red is slow, blue is fast. I have overlay plotted in green the MHT and the other splay faults which come out of it, which I have taken from the CCP and also the MOHO and the mid crust. So the main features that you see here is obviously low velocity sediments in the sub-Himalayas, in the Shivaliks. You see the MHT is a low velocity zone which runs across this region. Your mid-crustal discontinuity has a velocity of about 3.7, 3.8, and your MOHO has a velocity between 4.1 and 4.4. The MOHO that we pick closely matches the MOHO that Swati modeled from the stations. Obviously, you are collapsing structure across this region, and therefore there is 3D variations, and therefore you see this deeper segment of the MOHO somewhere in the middle underneath the sub-Himalayas, which is essentially a 3D effect on the structure. Now I'll move forward and look at the other cross-section, which is B1, B2, which is through the Pir Panjal Ranges, the Kashmir Valley, which is the northwest of our profile. Again, I'll show you the three things that I just showed you for the previous profile. Here is the receiver function spatial stack. We are at a disadvantage of not having stations in between the Pir Panjal Ranges and the Zanskar Ranges. There was a gap in our data. However, what we did was we filled it in through the work that was done by Mir et al. By putting in the receiver function derived depths in this region and then overlay plotted it along with the CCP stack that we have. Here again, I'll highlight the key features. Here, the crust is thicker underneath the northwestern segment. It's about 50 kilometers thick. It's a two-layer Indian crust, which goes underneath the Kashmir Valley and into the Zanskar Ranges. You have a deeper MOHO underneath the Pir Panjal Ranges, and there is an overall northward dip in the MOHO. And your MHT, although we do not have a lot of measurements in the middle, but by looking at the structure at the two ends, we think that the MHT is more or less shallow and absolutely flat across this region. If there is any ramp, like you saw in the other case, it would be almost beyond our network, which is underneath the Zanskar Himalayas. Now, if you look at the shear wave velocity structure, again, overlay plotting the MHT and the MOHO on top of it, this is what you see, that the MHT is marked by a low velocity layer. You have very little sediment underneath the piggyback basin, which is the Kashmir Basin, and your MOHO has a BS of about 4.2 to 4.4 kilometers per second. Now I'll show you depth slices of the 3D from the 3D velocity model, looking at the top 10 kilometers, then 20 kilometers, 30 and 40 kilometers. You have a pair of panels each. On your left is the absolute VS, on your right is the velocity anomaly. I'll quickly highlight the things that we see here. The first thing is that obviously the foreland basin and the Shivalik Himalayas have low velocity sediments. You also see this low velocity continuing across the Kishtwar Himalayas into underneath the higher Himalayas, which is marked by those two arrows. If you looked at the cross section or the map across the 10 to 20 kilometer depth, you would see that there is increasing velocity anomaly as you go towards the northeast. And the reason why this happens is, if you look at the cartoon that I've plotted on the left, is you are looking at a section through the Himalayan wedge, but you have more overburden as you go towards the northeast, and therefore you have higher velocities. If you look at the deeper section, which is 30 to 40 kilometers, you are actually looking through the Indian crust, and you have the flexed Indian crust underneath the Himalayas, and therefore to the south, you are looking at a deeper section of the Indian crust, and therefore you have higher velocities or high velocity anomalies. As you go further to the north, you are looking at the middle part of the crust, and therefore you have lower velocities. Now, the last thing that I'm going to show you about the structure is the average crustal VS across this region and the variation in the MOHO depth. The way we pick the MOHO here is by picking the 4.3 kilometer per second contour, which is plotted on the right. And what you're seeing is the depth to the MOHO, which is color coded. So red is shallow, blue is deeper. On the left, what you have is the average velocity from the surface to the depth of the MOHO. And what you can clearly see that lower crustal VS in the foreland basin and in the Shivalik Himalayas, there are no surprises to that. However, this low velocity continues in the northeast direction underneath the Kishtwar Himalayas. And you see a clear lateral variation in the velocity between the western Kashmir Valley and the eastern region, which you see both in the crustal thickness, where the thickness is larger underneath the valley, whereas the thickness is lower underneath the Kishtwar Himalayas. Now, the next question that we ask is, how does this transition across this region happen on the main Himalayan thrust? So again, just to remind you, the Himalayan wedge underneath the the southeastern or the eastern part is about 10 to 20 kilometers thick. It thickens as you go further to the north. The crust is about 40 kilometers thick. If you looked at the northwestern edge, the Himalayas are thinner. You have a flatter MHT. The wedge is thinner on top of it. However, you have a thicker crust underneath it. Now, the question is, how does this lateral variation happen? The way I'm going to address this is by looking at a cross section across this region, one along strike and one across strike. And what you see as topography on the top right is looking along that green arrow in the westward direction. So that is the direction in which you are looking at. I'll show you two cross sections across the green lines. This is what you see. So in the cross section which goes across the arc, you see a frontal ramp, which we also saw in the structure before. When you look at along arc, you see a lateral ramp across the structure, and you can see that there is a variation in the thickness of the Himalayan wedge, and that is what is actually facilitating the change in the depth of the MHT. So I've put in a cartoon on the right, or a schematic, which shows how this happens. This is exactly underneath the topography that I've plotted on top. What you're looking at is the Himalayan thrust is a flat across this region. It has a frontal ramp underneath the Kishtwar Himalayas, or the Kishtwar window. As you go towards the west, actually there is a lateral ramp, and that is where you have the low velocity anomaly running in the northeast direction, and the MHT shallows as you go towards the northwest. And where you have the lateral ramp, frontal ramp intersection is where all the earthquakes that you see underneath this region concentrate, which are plotted in green on the panels on your left, which are taken from Himanshu Paul's work. And this is the region where you had the 2013 Kishtwar earthquake. Now, what are the implications of this model? There are two broad implications. One is long-term in terms of geological shortening. So remember, I started out by showing you the topography across these two regions, and we said that we didn't know anything underneath these regions at that point of time. Now we do, and this is what we think is going on. So what we think is happening in the southeastern edge, or across the Jammu Kishtwar Himalayas, is the Himalayas are accommodating the long-term convergence through duplexing, or forming of the lesser Himalayan duplex, which is shown on the schematic on the top. That is one of the mechanisms by which you actually accommodate shortening. On the northwestern edge, I think what is going on is passive overthrusting, and therefore your MHT is flat, and it facilitates formation of the Piggyback Basin, where it's written MCT. That's the region of the Kashmir Valley. So the two regions across the northwestern Himalayas are accommodating convergence in two different geological ways, and they are most probably in slightly different zones of geological deformation as you see in the Himalayas. Now, in terms of the other implication, it's the structural control on fault ruptures, because if you have a lateral ramp sitting right in between where you have this mesoseismal zone of the 1555 earthquake, imagine if you were to break this region in a big earthquake, most probably this lateral ramp will play a role in modulating or controlling the rupture propagation. And this is something which we have seen in the 2015 earthquake. This is work done by Kumar et al., where we actually looked at sub-event modeling of the rupture on the MHT in the 2015 earthquake. And the earthquake, actually, the rupture went over a lateral ramp, slowed down. And you can see that in the plot on the bottom, where you can see the velocity of the rupture plotted as a function of distance versus time, and the rupture slowed down when it went over the lateral ramp. So obviously lateral ramps do play a role in how it modulates ruptures. And in this case, also this lateral ramp might play a role in a big earthquake, which might happen in the future. Now, finally, talking about the ground shaking from future megathrust earthquakes, how do we combine all of this information to understand that? There are two more things that we need to know. One is we need to know where is the edge of the active fault, or in other words, where does it go from being locked to creep, or in other words, the locking line. And you also need to know where the front of the active fault is. In order to do this, the reason why you need to do this is because then it will give you an understanding of the earthquake being either in sequence, which means it's going to break the entire fault and come out through the front, producing a much bigger earthquake, or it could be out of sequence where it short circuits through a fault within the mountain range and would be a smaller earthquake. So the way we do this is by looking at the GPS vector velocity vectors, turn it into a strain rate field, look at the the seismicity by detecting and relocating them, and then doing field work to look at the tectonic geomorphology, which Alex and Ashling did. So these are the three things that I'm going to quickly touch upon. So we turn the GPS velocities into a strain rate field, looking at the horizontal strain. What you see here on this map, on the previous map, what you see as the arrows are basically the GPS measurements taken from the literature. We combine this to calculate the strain rate field, where you're looking at compressions in plotted as the blue bars. And you can clearly see that there is a dominant northeast-southwest compression across this region. Although the GPS data is sparse, and therefore you wouldn't interpret anything which are at the edges. You would look at the region where you have all these circles, which are basically the earthquakes, which I'll come to in a bit. And you can see that the strain rates are large in this region, and it's dominantly in the northeast-southwest direction. Now, the next thing that we did was, obviously, we used the entire data set, and we looked at the smaller earthquakes. This is the work that was done by Shamim, along with Oyon. Here we started off by detecting the earthquakes. We detected about 1,068 earthquakes in the beginning. Then we picked the arrival times. An example is shown on the right on top for one earthquake recorded at multiple stations. And then we use these arrival time picks to actually use nonlinear the nonlinear location algorithm, to look at these earthquakes. At the end, we get 610 events between magnitudes 1 and 6. Mostly between magnitudes 2 and 4 are the earthquakes. You can see the P and S wave arrival picks on the figure on your bottom right. So once you have done that, we plot all of these earthquakes on the map. These earthquakes are plotted as circles on the map on your right. There are also these three focal mechanisms, which are from the Kishtwar earthquake and the two other aftershocks that happened after it. So as of now, concentrate on the circles that I'm talking about, which are color-coded by depth. What are the main things that we see? We see that the moderate to small earthquakes are primarily concentrated underneath the higher Himalayas in a band across that region. The depth of these earthquakes are within the top 20 kilometers, which tells you that they are all within the Himalayan wedge. And there are a few earthquakes which you see in red are within the under-thrusting Indian crust, which tells you that the entire crust underneath the Himalayas here is seismogenic. If I take a cross-section across this region to show you where the earthquakes are, you would then see their distribution as a function of depth. But before I did that, one of the things that you can clearly see, the region where I've written as creep, you have a very few earthquakes at the back. Also, you have very few earthquakes in the region which I say as locked. To explain this, let me use this cross-section. So here I'm using the 2D velocity structure in the background, along with the earthquakes which are plotted as green circles on top of it. So what you clearly see is that there are very few earthquakes in the region where I say is locked, which says locked. So there are no earthquakes in the frontal part of the MHD, and the back is creeping. There are a few earthquakes within the Himalayan wedge, but also there isn't a lot of earthquakes at the back. Everything is concentrated in the region where you have the frontal ramp, and that is what we think is the unlocking zone. So that is the zone where all these earthquakes are occurring. The reason why this happens is explained by this cartoon on top. Think of Tibet pushing over India, and the boundary over which this is pushing is marked as green, gray, and red. So as Tibet pushes over India, as the boundary is at a greater depth, because of the temperatures on that boundary, it freely creeps. Once it becomes shallower in the gray region, it starts to lock, or it's frictionally locked, and the front, which is red, is entirely locked. So as you push Tibet over India through the convergence, you are actually going to accumulate all the strain in that region, which is marked as those blue bars. And that is the region which will get strained and will produce all the small earthquakes. Till the time the frictional locking on the red boundary can hold, once it fails, it will move the big fault in the front and will produce a big earthquake. So that is the unlocking zone, also known as the zone of tapered slip, and that is where all these earthquakes concentrate. So you get a sense of where the locking line is from these set of earthquakes. Now, the last thing that you need to know is where is the front of the fault. And this is the work that was done by Ashling and Alex, going to the field, looking at where the rivers are cutting down and the topography rising, and they could actually pinpoint the frontal fault, which runs through the front of the edges. It's sort of blind. It is within those within the anticlines that you see in the front, and that is where the big fault is. So once you know this, you have an understanding of where the active fault is, where the back of it is, where the front of it is, and therefore then you can ask this question as to what will be the size of the earthquake if you move this entire fault. And this is a simple calculation which you can do, where you put in the entire fault area, you put in the slip that has been accumulated over the last 468 years. And you know that there will be an 8 magnitude earthquake if you actually move this entire fault. Now, the last thing that Ashling and Alex did by using all this information that we had acquired is they asked this question that if we move different segments of the fault, what will be the ground shaking on the surface? And here it's a combination of the seismology along with the field observations, which is then used to plot a simplistic model of the 2D structure going from the foreland basin to the Himalayas, which you see on the top, which is a cross section which you see on the map on your left top. And you plot the main Himalayan thrust, which goes through the Himalayas and then into the sediments in the front. Now, here is the scenario. So there are two different scenarios that we test. The two earthquakes that we know of, which happened in this century, are the 2005 Kashmir earthquake, which broke the surface, was a shallow fault near the surface, and the Nepal earthquake, which was a deeper fault, which did not break the surface, stayed at a depth of about 8 kilometers. So we use both these scenarios, and what I've marked as Nepal at depth is in green, that is the deeper part of the fault, as Kashmir in red is the shallower part of the fault. Now, if the earthquake moves either of these two faults, what kind of ground shaking do you expect? And that is something which Ashling calculated, and this is what you see. So the green one is for Nepal. Ignore the different symbols. The bold line is for the vertical component. The dashed lines are the horizontals. We look at the bold line. So you can clearly see that the Nepal earthquake produces ground shaking, which is a third of the ground shaking that you see for the Kashmir earthquake. Or in other words, if you move the shallower part of the fault, which comes close to the surface, most probably breaks the surface, will produce almost 3 times ground shaking than a deeper fault that you move. If you move the entire fault, then you get the blue line. So now what we then look at is how does this compare with the population density? So obviously the region where you have the largest ground shaking from the shallower fault is in the Indus Basin and the Shivalik sediments. That is basically the sedimentary basin or the Himalayan sedimentary foreland basin in the front. And that is where you have the densest population in the country. So you have the strongest shaking in the densely populated regions of the foreland. So this is where I'm going to stop. So I've told you about the 3D crustal structure that we obtained from the experiment. I've told you about the earthquakes, and then I've showed you how we combine all of this information to ground motion simulation. Thank you very much.
Thank you for this wonderful talk, Supriyo. I really enjoyed it. So the floor is open for questions. You can unmute yourself and please go ahead with your question. Okay, I will start. I mean, this is, yeah, please go on.
Someone has raised a hand.
Was he clapping? I thought he was clapping, no?
Daniel, Daniel, okay. Actually, I have one question.
Okay, go for it, Blush.
Yeah, Supriyo, thank you. It was very interesting. I just have one question. So you were showing at the end this ground motion simulation. I don't know the paper, but I mean, is there also some larger PSHA map for that area, or?
Yes, I think there is, but I've not followed these PSHA maps for this region. I know there are some maps which kind of broadly give you some understanding of what the ground shaking would be for a big earthquake. You have these broad zonations that we know of, and I think this is zone 6 or something like that. That's what this region is. But we haven't compared it with the PSHA maps.
Okay, and one more question. So here, so the Kashmir earthquake was in the front, so in that locked part, right?
Yes.
Yes, but what if it would? I mean, how would the ground motion change if it would be, if it would propagate further deep? I mean.
Yeah.
Because on this picture here, you are just showing the green one is the Nepal, which was deeper, and the Kashmir that was shallower. But
no, sorry, I didn't make myself clear. So we are showing all the 3 scenarios. What you see in blue is the entire fault rupture.
Okay. It says yes, entire
Okay,
fault
so
transit.
you
Yes.
see
Okay.
it kind of broadens. The peak ground velocities are similar to the red one, but it's broader, so it encompasses the entire green and the red regions. So the blue one is the entire fault moving.
Okay. Okay. Thank you.
But just a quick follow-up on this: do you think that the entire segment can rupture with the recent Kashmir
Yeah,
and Nepal earthquake?
that's a
There's
really good
still strain
question.
accumulation.
Yeah, that's a really good question, and that is something which we really do not know. So the two examples that we have, one is the Nepal earthquake, which broke the deeper segment, and the Kashmir earthquake, which only broke the shallower segment, did not move anything at depth. Whereas there are paleoseismological studies from the Nepal Himalayas which tells you that there had been big earthquakes which broke a much larger fault. So if you use scaling laws, it's most probably about 500 kilometers long, and therefore would most probably have broken the entire width of the 100 kilometers, and would produce close to 9 magnitude earthquakes. So this is Steve Wesnowski's work. The 1934 also broke the surface, which is in Nepal, the eastern Nepal. But I don't know if it moved the deeper part of the fault or not. So this is something which we do not know. And what I think the discussion that I last had with Roger was, and the paper that he wrote, a review of all of this, I think back in 2019, he thinks that you have all these 7.5 magnitude earthquakes at the deeper segment repeating one after the other, and then you completely transfer the strain to the front, and then you move the front. Most probably it always happens in two phases. So we still don't have an example where the entire fault moved, other than the paleoseismological evidences. So yeah, so it's an open question, and it's a big question in Himalayan seismicity at the moment. Everyone in the country is fighting about it. Will it be a 9 magnitude? Will it be an 8 magnitude? Will it break the entire fault or not? We don't know.
And
But
just a quick, yeah.
what is important is if you look at the ground shaking, it's not going to make a big difference. If it broke the shallower part, will cause similar damage as breaking the whole of it.
Okay.
Yeah.
And how are the local? I mean, I know this problem is really popular within the seismological community. How are the local people prepared for such
Yeah,
scenarios?
this is a difficult question. You know, one of the things that we have been doing over the last 6-7 years now with all these projects, with James Jackson, with Alex Coakley, every project has a component of the social sciences. We also have a current project which is running where we have this, and we through that we try and engage with the engineers and the local administrators and the people, and we have tried to build awareness. But as I understand, the awareness that you have, or the preparation that you have, is scattered. Most probably the bigger cities are better prepared, whereas regions which are remote within the Himalayas are not so well prepared. But again, the regions which are remote within the Himalayas don't have build up structures which are huge, whereas the cities do. So it's variable, and it's they all understand now, at least over the last few years of the work that has been done in India, that there is going to be a big earthquake which is going to be destructive. And there are lots of things that goes on around it in terms of preparing them for a big one. But how prepared they are is again a difficult question to answer.
Thank you. Any other question, please?
Daniel, this is Fabio here. Do you hear me?
Yeah, Fabio, I do.
Okay, thank you. Thank you for the very interesting presentation. It's very broadband. Have as a ground motion modeler, let me simply ask you, here I see PGV as an intensity factor, but have you been modeling the ground motion or just projecting with some GMPE? It's not clear to me.
Yeah. Actually, this is the work that was done by Ashling. This is a very simplistic model where she calculated these round motions. I can quickly move forward and show you a slide where it summarizes how she does it. I am not an expert on this. So she used this SW4 finite difference code to do this.
I got it.
So these
Now I
are
copy that.
basically the stuff.
But
Yeah.
let me tell you, so I think if you have reached 10 hertz as a modeling, as far as I see here, 0.110 hertz, well, if you move to acceleration, the profile that you're getting is going to be very variable there, and it will be very sensitive, keeping the fault scenario, but the rupture scenario will influence it. So the scatter of, for example, PGA will be much more variable than the PGV there. So maybe I hope that in the risk analysis, you computed it also using other intensity indicators. That's my hope, but I'm sure that you did it. Okay.
No, we haven't. So this is one of the things that we really wanted to explore through the current project that's going on. So this was a very preliminary estimate of what the PGV would be. This was a PhD work, a part of the PhD work of Ashling. With the current project, we really wanted to refine this and look at the other nuances. Again, as I said, I'm not an expert in this.
No.
We
Okay.
intend to learn this or collaborate to understand this. And this is something, maybe we will at some point.
PGV is a sound parameter, but it's, as you have seen, the profile is smooth. If you go to acceleration, it's going to be very vivid, and it's going to be very sensitive to the rupture scenario, not only to the fall. Okay, but thank you very much. Thank you.
Right. Thank you.
I have a follow-up question also, Ruby from Madagascar. I don't know if you know, like, for the ground motion simulation also, like, is it, let's say, rock based, or it's already implements, I don't know, side effect or something?
So we use a 2D structure across this region, where the deeper part is actually in hard rock. So we essentially use a velocity structure derived from our models. The shallower part is within the sedimentary rocks, which is kind of a lower velocity. So that's what we do. And then we look at what the ground velocities would be at the surface. So they are, obviously, when you are looking at the ground velocities within the Himalayas, they are on a different velocity structure than when you are looking at it in the foreland basin. So that's what you're looking at. But we do not have the near surface effects in it, if that's the question that you're asking. No, we are not looking at local side effects at all.
Okay.
So this is all on bedrock level.
Okay, thanks.
Yeah.
Any other question? A quick one. What's the maximum expected magnitude within these?
Yeah, see, that's the question that I was trying to answer. If you break this fault that you see on the screen, if you start from where you have all these small earthquakes concentrating, which is most probably where it's unlocking, going from creep to locked. If you start from there, break through the male frontal fault, which we think is the one which is active in the front now by looking at all the geomorphology, then you are looking at 8+ magnitude. That is what we think. But here the assumptions are that you are breaking that entire red oval that you see on the right. So you have a 250 kilometer wide, about 100 kilometer across, long, and 100 kilometers across fault that you are breaking with, and you are releasing the entire slip that has accumulated since the last earthquake, which is an estimate made from the GPS arc normal convergence of 11 millimeters per year. So if all of these are true, then this is what you are looking at in terms of magnitude. I've used 2 to 4, 10 to the power 10 as your mu, because that kind can be variable. But yeah, so 8.5 is the maximum that you're looking at.
That's big.
Yeah, and that's a really big earthquake. Yeah, for a region like this. Yes.
Thank you. Any other question? Okay, it seems everyone is happy. So I would like to thank you again, Supriyo, for this wonderful talk, and for everyone for attending. So next, I think our next seminar will be on the 19th February, and you're all welcome to join us again. It will be given by Blash, who is also attending today. So see you next time. And
okay, thank you very much, everyone. Yeah.
Thank you.
So can I log out now, Daniel?
Yes,
Thank
yes.
you. Okay.
Have a good evening.
Thank you.
Thank
Bye.
You too. Bye.
you.